Your army voice.
All right. Welcome, everyone.
Man, we've got excited audience members already.
I know, this is great.
Heck yeah.
I invite everyone to start getting seated, get comfortable. I know that there was a wonderful session before this. We'll do our best to follow up after that, but thanks everyone again for joining today here for the Digital Engineering and the Future Workforce panel. I think this is going to be a really fun discussion. We had our prep call earlier, and I think someone on the panel said they couldn't wait to nerd out, so I'm really excited to do that. Before we get into it, just some housekeeping here. I would love to thank, and on behalf of the conference, would like to thank today's breakout session room sponsor, Oracle Cloud, so thank you for sponsoring this and the conference broadly. For the audience, questions will be submitted via question cards. Fill them out as soon as you have a question. Don't wait until the end. If a great idea pops up, jot that down. Pass them to the aisle, and someone on the aisle will raise your hand so we can get the cards. And this session is eligible for CE credits, continuing education credits. If you're interested in obtaining them, please be sure to have your badge scanned at the end of the session by the summit staff in the back of the room. An email will be sent out to those scanned after the summit is over. For press and media may be present during this session today. And what's happening after this is just join us in the Maryland foyer for a networking and exhibits break. So, got that out of the way. But again, thank you all for joining us. Digital engineering seems to be a really hot topic these days. It's a controversial term. I do feel like personally digital engineering is something we've been thinking about for a long time, but it's resurfacing just given what we're experiencing from a resiliency perspective. And not only the industrial base, but just how we perform our engineering life cycle. So really excited to have everyone here today on the panel. We'll do 5 minutes of introductions, we'll move into some great dialogue, and then we'll invite you to have a dialogue with us. So, rather than me introducing these folks with a fun, long blurb about each of your backgrounds, everyone's got the backgrounds in the panel, in the pamphlet, you've seen them on the website. We're gonna do a fun exercise. We need your participation today. Please participate, otherwise it's really not enjoyable. We'll do a truth and a lie for each participant here today. So I will give 2 facts, and then I will ask if you think the truth was the first one or the lie was the second one. We'll have people raise their hands. So Sarah, the Senior Associate of CSIS here for the Aerospace Security Project. I'll start with fact number 1, or I would say associate fact number 1. Sarah Monero was the primary drafter and negotiator of the Space Force and Space Command legislation for the House Democrats. That's fact number 1. Fact number 2 is Sarah Monero is a renowned artist in the DC community, and her artwork has been displayed in the Torpedo Factory. So, everyone ready to participate? All right, fact number 1, truth. All right. Fact number 2, truth. All right, we're doing well. Great job, everybody, for the most part. So for those who voted fact number 1, all of that was almost correct, except it was the Republicans on the House. So you can thank Sarah Monero for the Space Force, essentially. So thank you again.
The media is present, so I will try to make this as unremarkable as possible.
Okay, great. So we have Mark Honda. Mark Honda is the Chief Engineer of the Space Systems Integration Office for Space Systems Command of the U.S. Space Force.
Thank you.
So, fact, that was a fact, by the way. We're not there yet. Fact number 1. So Mark previously, interestingly with his name, worked for Honda as an engineer at the start of his career. Fact number 2, he holds 2 patents in the area of power engineering. All right, so fact number 1, truth. Fact number 2, truth. Wow, all right. We're gonna have some good Q&A, I think, later. All right, Torsten. Torsten is the Senior Vice President and Chief Supply Chain Officer for Honeywell. Fact number 1. Torsten actually has an MA in art history, and it wasn't until later in his career that he was inspired to work on engineering because he saw that as the truest art form. Fact number 2, Torsten led the development and manufacturing of the Falcon Heavy rockets during a critical time at space exploration technologies. Fact number 1, truth. Wow, Torsten. Fact number 2, truth. All right, it was fact number 2. Torsten was the vice president of supply chain at SpaceX during a very critical time in the organization's history. It wasn't just Falcon Heavy, but Starlink, along with many other critical assets produced during that time. And now we've got Jared, last but not least. Jared is the senior strategic advisor to the director of the Defense Innovation Unit. Fact number 1, Jared was an intelligence community postdoctoral fellow with Professor Chris Ray at Stanford AI Lab. Fact number 2, Jared was point guard for the, let's see, sorry, I'm reading his bio. He was point guard for Cambridge University basketball team. Fact number 1. Fact number 2. Wow, Jared.
I'll take that.
So it was fact number 1, that was the truth. He actually played for Oxford. He played for Oxford. All right, so now that we've gotten that all out of the way, this is about to be a really fun discussion. So I invite all of you to respond to my initial common question, which is just about digital engineering at large. I think people are really excited about digital engineering because it inspires a change in the future. It inspires like how we operate. It changes the paradigm for how we think about day to day and how we bring things to life for not only national security, but just broadly resiliency. So I'll invite, and feel free to just jump in when you want to. I'll pick on you later. But question number 1, how can we reimagine interagency, public-private, and ultimately allied partnerships when we look at digital engineering? And we look at achieving resilience in our critical emerging technologies. So I know that was loaded, but we're starting with a vision here. So does anyone want to respond?
I mean, I'll start, because, I never have a problem speaking my mind one way or another. Digital engineering in the Department of Defense and the intelligence community has been kind of a hot buzzword right now. I will tell you that, starting in basically like the 2016 timeframe to now, there's been a lot of attention paid to it. There's been a lot of, when it's gotten to the point where the Office of the Secretary of Defense for Research Engineering lays out a strategy, you're probably already 5 years behind where you need to be on it, quite frankly. Over the course of my career, I'm a space nerd, unapologetically, and so, I've done a lot with space, with missile defense, with our nuclear weapons enterprise, and these are really strategic level assets, right? Where there can be very little risk tolerance, where there is no real opportunity for comprehensive testing, and if you want to drive flexibility, you need to be able to do that very early in a program. And digital engineering kind of enables all of that, right? And so from the very beginning, space is an unforgiving environment. It is not the case that you build a satellite, you launch it, or at least historically has not been the case that you build it, you launch it, and then you tinker with it. You bring it back down, that's not how it happens, y'all, right? Like, these are multi-decade kind of programs that you need to think about in the beginning. So digital engineering, digital twinning, all of that mod simming, being able to do that with multiple sources of data, multiple kind of areas of truth to be able to manipulate that early and define those requirements early, and then be able to do those engineering trade-offs in a sensible way that enables you to build that infrastructure, but then layer on flexibility while also maintaining, quite frankly, a clear focus on supply chain security and capability and capacity. And those are all things that will reduce risk in a program, but also enable it to be able to address the threats of the future. And that's really what I look for in kind of digital engineering. And that is said by an artist and a hill rat, which means, if it's so simple that an artist and a hill rat can do it, hopefully the rest of the government can figure it out.
I love everything you just said. I think you pointed out a couple of like fundamental things. Like it's not just about efficiency. Because a lot of people think about that immediately when they think about digital engineering, like, oh, my modern sim is going to help me do this way faster, or like in an environment that might not be tested in the real space environment, but something that is close to it, or I can have resilience in my different design options. But you talked a lot just now about like mission benefits, and you talked a lot about quality benefits, and I would invite the rest of the panel to talk through that as well. Like when we think about mission benefits and quality, like just like pull on that thread, and how can we actually bring that to life?
I'll go then. Again, my name is Mark Honda. So I'm Chief Engineer for Space System Command, where we do all the Space Force acquisition for space. And you're right, space is hard. Typically, we get one chance to do it right. Once you light that rocket, you're committed. Now, we are looking at ways to do on-orbit servicing. That's a few years out. But yes, I think it is a force multiplier to do digital engineering correctly, which means models have to be at the correct fidelity and precision. Digital twin, I'm kind of allergic to that term because I ask, is it an identical twin or is it a fraternal twin? and because a lot of people come to me with high fidelity models, which I'm good with. But until it's validated or correlated to something that's actually, it's supposed to be a model of, I have a hard time calling it a digital twin. So I can work with the rest of the other models out there. So I do systems of systems engineering. And so the digital engineering environment that we're trying to establish in the Space Force, we're trying to make it so we can federate with all our mission partners. We're trying to federate with the contractors, and so we're trying to create that environment. And really, it's the industry that's got to come forward with the models, right? The government can come up with their government reference architecture, but we really need truth from industry. And so you got to have accurate models, not marketing models, okay? And I'm an engineer, right? And so, I want to get things done right the first time. I want to go faster. We're going on higher tempos, right? Shorter satellite missions, more opportunity to innovate. So digital models will allow us to Monte Carlo different variations, different capabilities, different combinations of assets. So, I want to echo her sentiment that this is really a force multiplier if we do it right. But we need to partner together, government, industry, nonprofits, and work together to create that ecosystem that holds together. We got to be compatible. We got to be interoperable. MOSA is another buzzword out there, but there's a truth to it, right? We got to have common ontology. We got to be able to speak to each other. If our models don't work together, digital engineering is going to be a really tough field to plow. So I ask everybody, let's check our egos at the door. For me, it's about the warfighter, right? So I want to bring everybody together so we can work together. It doesn't matter who you are. We should be able to plug and play. Some models will be black boxes. Great. Some models need to be modeling down to the trace because microseconds matter. So we got to have the right models for the right applications.
I think this is where I come in, because I'm the industry guy here.
There you go.
So, look, about the benefits, I don't think we have to debate that. That's a good thing. It's cheaper, it's faster, you can simulate things. You create answers faster than in the real world. And there is a lot of experience in the industry in other areas outside of the space world. If you think about just the chemical industry, they've been using these type of technologies for 25, 30 years, and they have been using them because otherwise people die, things explode, things don't work. It's very, very similar. It's not different, but the same principles have to apply. That you have to understand what's the foundation of these models, what the physical connection to the real world, and you have to trust your data. If the data infrastructure is somehow fuzzy or somehow not clear, then unpredictable things will happen, and that's what you can't live with. So you have to agree on what's the common thread, how do we interpret certain data, And then there is different people own different models sometimes. It happens in our industry all the time that somebody has a very specific model for a catalyst and that's IP protected. But still it is useful in a larger industrial environment for the bigger community. And I think that's very much applicable to your use case too.
Yeah, so some of the things that I'll add are that I will couch in a story about my PhD, which is the first useful thing I will have ever done with it. So let's start there. Some of the work that I used to do was designing combustion chambers. And when you're designing a combustion chamber, you have to care about lighting things on fire. And lighting things on fire means that you have chemical reactions that are going very fast, and you have fluid mechanics that are going slower, and you have heat transfer, heat's moving around even slower than that. Sometimes 1 billion times slower than the chemical reactions are happening. And being able to design a system where you can't always get experimental access to it because, say, it's inside something, you can't see it, there aren't good experimental methods to get at it, requires digital engineering. So, people have been trying to simulate fluid mechanics and turbulence and reacting flows and these sorts of things for ages at this point. We've made tons of progress. At the same time, to accurately simulate some of these things, it requires millions of core hours at a national lab. You physically can't do it on commodity hardware, on hardware you'd use for kind of everyday design. So there are these potential benefits in interoperability, being able to separate your design site from your test site, from your fab site, so being able to say, look, I designed this thing, now I want to make it over here and make it over there and make it over there, instead of having to have all the equipment in the place that I was designing. And doing things in harsh environments where there's certain environments you're just not going to be able to get at experimentally. But what I think is both interesting right now in terms of why are we having this conversation right now, there are a couple of reasons, but one of them is the substantial increase in capacity of kind of relatively commodity and available compute. So our simulations are a lot better now. Not the ones that are on millions of cores, but the ones that I can do on maybe a node or a cluster or a smaller group of computers. They're way better than they used to be, to the point where there are 0 to 1 types of things that we can do now that we didn't used to be able to do. But what that also means is that we have to be able to figure out where do we optimally simulate and use digital approaches versus where do we test. And it is not always obvious when you do one and when you do the other. And to the point that was said earlier, there are some benefits to testing with real things, because you find out that, hey, that little divot that's in that part over there that didn't show up on my digital twin, well, that causes the entire thing to explode. So to do this effectively, moving from the should we do it to the how do we do it effectively, a lot of the how is figuring out where is that envelope where modern compute growth is going to allow us to do things that we couldn't do before, and given that, how should we optimize our testing cycles to be able to test only when we need to, but make darn sure we're testing when we need to. That's the art of this, which is exciting and kind of for the engineers in the crowd where a lot of the exciting work will be done, I would argue.
So just to pull on that thread, Jared, since you're already talking, you talked a little bit about it at the periphery, but how does AI help? I know you talked about refining models and growing models, and does it matter? I remember at the days at SpaceX, you said it's always the little thing. It's always the little thing that either pushes schedule, or it's the thing you got to change in the drawing because there's a shortage of supplies. And I just wish that there was an AI way to help me when I was looking at a composite lock, or I was looking at a screw, to help me understand the real life availability to me as I'm bringing to life something that, frankly, in the time of needing resiliency and rapid response to things, at my fingertips immediately. So how can AI help with that?
Oh, it took us only 2 questions to end up in the AI world. Yeah, that's interesting.
Yeah, I would say that in general, and this is my general rant about AI systems, which I will spare you the majority of, if you don't have a clearly defined task, a clearly defined metric for success, and a clearly defined baseline that you're comparing against, you're not going to be able to derive value from things. So in general, when you're looking for those areas, I would generally look across the entire kind of soup to nuts process of designing and building something, and look at all the places that you're spending time and energy or incurring suboptimality where you might be able to do better. And so some of those places that I've seen in my experience have been, and I'd be interested in what others see. There's certainly cases where, look, there have been 9,000 articles published on something. No one's going to read all those things. Just being able to pull out, and prioritize information and be able to say, look, there was actually data about this. Here's what you should do. That's helpful. There have been some folks who have moved into, being able to automatically do, help suggest, the next experiment. So I've done 3, whether that's a computational or a physical experiment, suggest the parameters of the next one and reduce your experimental costs. 2 that are close to my heart, when we have extremely complex models, our models of the world are outside of, things like Newtonian physics, very imperfect, so we always have to cheat. We always have to, everything that we do in numerical computation, where we're doing things like, fluid mechanics, I laughed when I was in grad school for the first time, said, okay, so my entire degree is in fake derivatives. Like, this is what I'm doing. I'm taking fake derivatives. Fantastic. So being able to, some of those terms that you have to put in equations that you can't solve to fake it, we can fake better with AI models, just because of the mathematical structure of them. And so there are places like that. Diagnostics as well. So when we're looking at trying to do experiments in harsh environments, and we're getting very low signal to noise ratio on a particular diagnostic we're doing, denoising is good. Other places to look, I would argue, are controlled complex systems, potentially, some of the robotics pieces. So it's not going to be I throw AI at something and it works. It's going to be I have to have thought intentionally about where are the places that I can actually derive value from computationally driven approaches, and where is the current state of machine learning, AI, advanced computation, qualitatively different than it was 5 years ago, and how do I run those experiments to convince myself that those things are actually going to add value in a way that doesn't bust my budget, and that's really the art of this.
But if you think about not only how to design things, but also how to make it. As an example, let's take an APU of an aircraft that has 1,000 parts on it. This unit has 1,000 parts. So I have probably 200 suppliers that are somehow involved in this. And I know what they're doing, but then I need to know what the supplier of the supplier is doing, and how this all trickles into all the way to the steel mill. And to understand these relationships, it's practically impossible if you don't have an AI model behind that, because there's not enough humans in the world who can get, the number of permutations is so high that you can't get into this. So if you want to understand what your supply risk actually is, and that's also a topic, are we capable of making what we think we can make, and how reliable are we, and how resilient is this, to get into these tier 8, 9, 10, 11, 12, that's, in my opinion, it's impossible without proper AI models.
I think what's interesting from my point of view on when you look at strategic systems and the application of AI, is a lot of people think about leveraging AI for large data, computational kind of anomaly detection or analytics. And there's no doubt that computers can crunch through that, identify and kind of characterize and crunch through that quicker than humans in almost all circumstances. But speed isn't necessarily the metric that you want to measure everything by. So being a nuke nerd, right? Yes, could you use AI to help detect a launch, characterize a thing, even kind of build out rudimentary COAs? Sure, but you're always going to want a human in that loop, right? It is not the case that AI is going to obviate the need for judgment or obviate the need for actual real intelligence by a human. And so in some instances, in your kill webs, in your engagement chain, you want AI. That tends to be, I think, very left of launch, where you're kind of looking at what the heck's going out there and figuring out anomaly detection. But what you actually want AI to do at the same time is to slow down when you need a human to make a judgment call, to be able to give humans more time to make the correct engagement or judgment call. and then you can speed up on the engagement when it needs to happen, and then you can redo that cycle. And hopefully, again, as a missile defender, hopefully you have multiple shots that you can go, you can get through that cycle quicker in the 25 minutes that you have to be able to decide whether you're engaging or not. And so the other interesting thing for me on AI is how it speeds up some parts of your decision process, but it slows down other parts of your decision process. And that it's not just a binary kind of acceleration based off of a linear relationship to compute, which is advancing and amazing, and then hopefully we push more kind of that capability out.
Yeah,
So,
go ahead.
If I continue to pull this thread, and I violently agree with everything everybody said. I think what this does is it amplifies the importance of the engineer. AI, digital engineering, these are all tools, right? The reason we pay plumbers a lot of money is because they know how to use their tools and we don't. They know how to use it efficiently without making the problem worse. So the engineers, doesn't matter what your discipline is, if you're employing digital engineering, if you're employing AI, you have to use them as tools to be force multipliers to get rid of the mundane work and focus on the critical things that require intelligence. The decisions, understanding what that anomaly is, because the AI hasn't seen it before and doesn't understand it. So I urge you to be critical thinkers when you use these tools. That is what sets us apart. We have massive amounts of intelligence and creativity within our community, and I deeply respect that. But we need to be smarter in how we apply everything so that we get that innovation, we get that force multiplication, right? Instead of having 10 engineers work on one thing, allowing the tools to do the Monte Carlo, to do the various scenarios, to do the kill webs and analyze it faster and distill it down so where you can start saying, okay, these are scenarios we need to focus on rather than analyzing every scenario out there.
Yeah, I mean, we pointed a lot to just the need for, and it's a great segue to how digital engineering can help with risk mitigation as we become in this ever-evolving, continuously global, complex economy, and we're experiencing conflict just bubbling up everywhere, geopolitics are increasing. Like, how do we use, or I think, Mark, you said it well, this is a tool, this is a subset of all the things we have at our disposal to think about how we bring to life the things that are agency today. Like, how do we think about digital engineering in the context of risk mitigation as we do build things? And if you look at this panel here, you've got Sarah, who's like the strategic policy maker. You have Mark, who represents the system of record. And you've got Jared, who represents like the innovator, AI expert. And then you have Torsten, who represents, frankly, the builder. And it's a lot of what we're relying on as a nation to bring to life these things. So Torsten, you were talking earlier about just thousands of pieces and like the ability to manage. I mean, I don't envy your job at all. Managing so many complex systems that are going not only to our governments, but across the globe. So how do you think of digital engineering in the context of risk mitigation?
I do like my job.
I'm glad you do.
No, it's a fun job. And well, look, we always have more information than we can actually consume, usually. And so, because there's not enough people who can look at data, who can make the right decisions or whatever. And what we're talking about is helpful with this. And I agree with Mark, it's a tool. It's one of the tools, but it's a very powerful tool. So we can use this. That's one aspect. For us as a producer of physical hardware that's critical, it's very important that we can look around corners, that can anticipate things, that we know if something is going to work or not going to work. That's more on a strategic aspect. So it allows us also to say, should we design our production network differently? Do we still rely on one global supply chain? Are we running more a regional or a local setup? And that's helpful. I think it's a really helpful tool in decision making. But if you think of the pure process of making something, digital engineering allows us to act early in the process because we know what's coming. We have early visibility of what are different design options, and we can provide input of making this better and simpler and easier. But then when it comes to actually manufacturing it, we have a significant shortage in this country of machinists, for instance, CNC machinists. The average age of a machinist is 52. If you think we have a problem right now, wait a couple of years, and then we have a real problem. We just don't have enough people who make things. Now, and making physical hardware is a complicated process. It involves a lot of people who look at things, and we utilize a lot of AI tools, vision-based AI tools, to just understand, is this a correct, surface treatment? Do we have scratches? There are very, very specific things where I used to have 5 people doing it, now I can do it with 2 because I have somebody or a machine that helps with this. So, we look at this, it's very positive for the industrial base because it provides an option value. It helps us be more resilient. It helps us to anticipate things. And I do think that's why we're going into this. But we are still early in the real AI world. But the connection between engineering and manufacturing and operations, that's super, super powerful. But it requires a lot of things. It requires that people who used to use paper, they are now very comfortable in using digital tools, and that's not always the case.
Yeah. And if I can add to that, build on 2 things. First of all, this piece of, the example of using computer vision to say detect cracks, detect malformations in the manufacturing process. This is one of those cases where there's a very clearly defined metric, there's a very clearly defined test, it's very clear what the business value is, and there are some of these things that are slam dunks. It's like these will work. And there's another, I think, implication here though, which is we can use digital engineering to help us design in a better way, to design in a way that maybe I can substitute in part X, part Y for part Z. There's also a downstream systems engineering aspect to this, which I think is sometimes overlooked, which is if I know sometimes in the engineering world, I say I have to design something with a certain, to be with a certain tolerance, and I have to design something with a certain tolerance because if I don't, I'm worried about something else about the system will explode. And I can't source the thing with the tolerance that I need. So what are my other options? Well, sometimes one answer would be, I'm up a creek. Another answer would be, if I can constantly monitor for that explosion I'm worried about, I can use something that's maybe not as finely toleranced, but I can put in a cheap little sensor and a little bit of cheap computation, which now we can do. And I can, from a systems perspective, then design and say, okay, let's substitute out, not this, class A part, but maybe like this class B thing plus a sensor that is constantly being monitored. And if you were going to do that for 100 sensors, you wouldn't have the humans to do it. But if you have the computation and some of the AI pieces to be able to constantly monitor some of these sensors just for like, hey, that looks bad, you start to open up a new part of your design space, which is something that's really important from a resiliency perspective.
I feel like Mark and Sarah are going to have a lot to say about that. It is interesting because up until now the discussion has very much been around what you said. It's like we have this drawing, we have to build this thing, we know what this thing is, but now you're entering this other extension of that, which is, what if we don't know? And we're trying to bring something to life and we want a sensor-based environment to imagine not only what we want to build, but what is possible to build in response to this mission need, and not getting so solution-focused immediately, using sensors that are available to us. So that's really interesting. So I'm curious with the two of you, like, what is your response to like the two of them talking about the realm of the possibility, and how, especially with you as like a systems of systems thinker, like how do we grapple with that and think about interagency partnerships through something like this?
The first thing that comes to mind is war games. Just being able to take the digital environment, digitally simulate either theater or wider conflict, and seeing how resilient we are to model the kill chains, the kill webs. See what works, see what doesn't. Get operators into the loop. Get junior, CGOs who haven't really bent metal or sat in an operating seat, and just kind of open the aperture, because a lot of them come in, They're very focused. They got the event horizon of a cicada, and we need to just open that up more, right? I think what it does is it helps the creative thinking, just being able to see possibilities. I think the human mind is a wonderful thing when it can widen its perspective. And I think these digital tools, the AI, can accelerate that.
Agree with all of that. Also, I think that when you start to leverage digital engineering and the requisite tool set that's associated with that to really imagineer kind of where you want to be in the future, what ends up happening is I think you actually end up seeing a higher demand for different data sets and different kinds of phenomenologies. And I think you end up seeing this, I think you have started to see this in the space world, where, I mean, you're literally getting just a tremendous amount of data that's coming down from space-based assets, whether those are commercial or NTM or, you know, a lot of that has been restricted to a couple of different kinds of phenomenologies. And what you've seen over the past few years are different kinds of phenomenologies that are starting to open up, and there being a commercial marketplace for that, but then also seeing operational kind of use. So things like RF mapping, things like domestic space synthetic aperture radar, which the US has historically driven out of the US market, has fled internationally. Hyperspectral as a commercial offering, right? And so now you're getting to the point where the compute and the algorithms have been kind of developed, and that infrastructure layer, right, has kind of been developed so you can bring in the existing data sets. So the next question becomes, what are the other data sets? What are the unique data sets that you can bring in? You have to start all over with kind of your training data and kind of that requirements and metrics. But again, you can kind of speed that up. And I think that will be interesting to see, not just how can we do more, better of what we have now, but how does that free us up to look into more and different for the future?
Oh man, I'm imagining all the RF mapping and how it could involve digital engineering. There's just so many things when it comes to sensor-based networks that really make things a reality. Everything from what you mentioned, space data, to things like trade data, to things that represent, frankly, like some of the regulatory activities that we see too across the landscape, and trusted vendors associated with production. So no, it's a helpful response to think about how you're thinking about the vision, how Torsten's thinking about, okay, I've got to build these things now, and then for you two, like, okay, how do we think about the broader architecture? So I know we've got about 15 minutes left, and I'll invite you, and I'll just say, you know, one at a time, what you want the audience to remember about, like, given your perspectives, how they should interact with this. I mean, how many people in the audience are industry? Okay, it's mostly everybody in here that are involved in the national security community. They want to be a part of our resiliency. They want to be a part of this like amazing infrastructure that involves everything from space data to manufacturing to designing and AI. You can't forget AI. So I'll just invite all of you to have a closing comment, and then I'll do some Q&A from the audience. Do you want to go first, or Jared, do you want to go first?
We should start that way. Come down.
The thing that I would take away from this conversation at the time that we're having it is that there have been recently, there are, and there will continue to be qualitative changes in the capabilities that we are able to bring to bear from a digital engineering perspective. The value that we'll be able to get from those, from both an industry perspective and a government perspective, are going to be gated on a couple of things. One of those things is being able to efficiently use them in the right parts of a design cycle and convince ourselves that replacing whatever other design cycle we would use is not just going to be cost efficient, but it's also going to be, going to provide the functionality we need. And second, I would emphasize something that was said earlier and paraphrase a former colleague of mine. So Kurt Langlotz is a radiologist at Stanford, and I don't know, for those of you who follow the AI Twitter wars, there was this big debate for a while about that someone saying, hey, radiologists are going to be just out of practice in 5 years. AI is going to take all the jobs. And I think at the end of the day, the consensus has become, both from technical reasons and for practice reasons, the right response to that kind of argument really has become the radiologists that are able to use AI systems are going to be better than the ones who don't. And that is likely to be the case, as was said earlier, with digital engineering engineers who are able to use these systems effectively in the context of both designing systems, manufacturing systems, test and evaluation cycles, interoperability with other systems, are going to be fundamentally force multiplied compared to those that don't. And we should think about not only how do we acquire and use use tool sets to do this, but also how are we building our human capital to be able to do that within our organizations, both in the government, frankly, and in industry. Because if industry does it and government doesn't do it, government won't know how to receive it, and vice versa. If government doesn't and industry doesn't do it, we're going to be asking for a bunch of things, and you all are going to be like, what are you asking for? So that's my thoughts.
Well, I think that ship has sailed. We are using it in the industry. I mean, we've been using it for quite a while, and we've learned a lot of things. But it is the future. It is because it allows us to do more things. Because it allows us to free up human capital to do more value-added things, to eliminate things that are not really useful, and it just require a lot of work. And so that's why there is a fundamental benefit in doing this. It's going to happen. Embrace it. We need to embrace this. We need to find a good way to work together to do this. But there are ways, there are platforms, there are things that help us connect things. I'm very, very positive, and it is really a transformation that we are seeing right now, and everybody, and there are people both in the industry and in the government that are at different speeds, and that's very natural in these transformation processes. We have 100,000 people in the company. 50,000 are in operations. They are in my world, so it's not easy you can't flip a switch and say, well, you're digital now. That's not how this works. People have to learn things. You have to train them. It's a process. It will take time, but there's no turning back. It's going to be the future. That's very, very clear to me.
So the general keeps telling us we need to exploit, buy, build. Exploit what we have, buy what we can, build what we must. This is an opportunity for industry, smaller businesses, to become an influence, to become a participant. If you have something that we can exploit today, if the government, another part of government's using one of your tools or your offerings, we're looking to use that, right? If there's something that's out there that can be quickly adapted, that's in the buy category, looking for that, and then we will build what we must. We got to get through those first two things. And we have something we call the front door. It's under the Commercial Space Office under Colonel Rich Nisley. You can go to our SSC front webpage, look up front door. That is where you bring all your offerings, right? All your ideas, and they sit there and they take everybody's ideas and they rack and stack and they see where there are synergies. They could even possibly get people to partner together if two people have half of the solution. So that's what I want to leave you with is we're looking for that innovation. We're looking for that partnership. We're trying to go fast. We got a fight that's coming really fast. And, for us, it's about the warfighter, right? If you can help us make it so that our troops, our sailors, our airmen, our Marines, our Guardians all have an unfair advantage over the competition, we want to hear from you.
Yes, I also welcome our robot overlords. Just like Thorsten. We're good. It's going to be a better future, y'all. Look, at the end of the day, these are tools. The technology is getting better. We'll see if the government is able to make systems and inroads to be able to catch that and do great stuff with it. But again, they're tools to be used by humans, right? Like, in no circumstance, I should not say that. There's probably like a non-zero statistical chance that at some point the entire population gets wiped out. But it's pretty unlikely, right? Like, it's probably pretty unlikely. So in most all circumstances, these are tools that are supposed to make us more efficient, better, and hopefully more creative. And that's something that we should be excited about.
I just heard the world was ending throughout that whole thing, but okay, so we've got some really great questions. No, it was a hopeful the world is ending kind of thing. It wasn't bad. So how do you, okay, this one is really good. And I know we've only got about 10 minutes. I wish we could be here longer. This has flown by. We've talked a lot about like some of the really like structural things with engineering. We've talked about production. We've talked about simulation. We've talked about sensors and like different data assets. What we haven't talked about, which is the second part of the title, which is the workforce. And so someone brought a great question, and you have all been leaders in this industry for some time. And I think this is a question that touches everyone, whether you're explicitly in workforce development or not. So how do you change organizational culture, specifically in the government or industry, to enable digital engineering? We talked a little bit about the engineer, but just like culturally, we talked a lot about like, don't be worried about the robots, they're not gonna take your job, but like even just strategically, like how do we think about shaping the workforce around this new life cycle? And even from a policy perspective, it could be interesting to think about like how do we invest, where do we grow capacity? So curious if anyone has immediate reactions to that to share.
Yeah, I do. So I've been in the industry 15 years, so FFRDCs for 12. Courage. Everybody wants to be a leader. And I keep coaching my proteges. You can be a leader from the middle. You set the example for others to follow. You see a tool, you can use it, you can exemplify it, you can teach your peers, you can teach your leadership, you can teach your juniors. And you start, it's kind of like, I remember back in the day, Apple was putting computers in all these schools for free. Microsoft was like, take Windows, and it's basically, it got to the point where when you went to work out of school, you want to use Excel and Word, not those other programs that people have probably forgotten, Lotus and WordPerfect, right? Because you got used to it. So you can be an influencer. You don't have to be a manager. You don't have to be a quote unquote leader. You could be the example for others to follow. And I'm a big proponent of that. I've been in leadership for a good part of my career, but a lot of it has been setting the example for others. How would I want my juniors to act? How do I want my peers to act? Be that influencer, have the courage, right? Gotta be, respectful, right? And, lift other people up. And the more you do that, the more people listen to you.
This will be an astonishing fact, since I am partially responsible for writing the legislation that established the Space Force. But also, I will say this. Changing organizational culture is not something that can be legislated. It is a thing that rests on individuals. It is a thing that rests on the organization, which is made up of individuals. One of the least effective ways that you can go about changing an organization culture is to attempt to pass a law. There's media here, so I will not go into the rest of it. But I mean, at the end of the day, DC is a pretty transactional town. It's a pretty baldly transactional town in some respects. And it is refreshing to meet people who are interested in not just the organizational change, which quite frankly needs to happen, but also in people just supporting authentic people. Because if you're in this audience and you're in this ecosystem, or you're up here on stage, you're probably not just doing it for the dollars. You're probably doing it because you believe in American exceptionalism, because you are trying to leave a better community for people to come after you. And that's great, and we should celebrate that. And that needs to resonate with people. But yeah, I mean, I think one of the least effective ways of doing that is just by like attempting to legislate it. Although, Space Force, woo-woo. All right.
Yeah, I'd say the last couple of years I've spent trying to think about, particularly in the context of AI systems, how do we change organizational cultures to adopt these things and use them in the ways that are effective. And I won't give the entire spiel, but I'd say there are a couple of things that I would take away. One, and a lot of these will be obvious, but one is find things people hate and try to get rid of them. So when you go into an organization and trying to automate or enhance or whatever the things that people actually like doing, like they're going to fight you. If you find that spend time finding the things that people absolutely hate doing, and try to work on those things, you tend to get more buy-in organizationally. Thing two is resourcing experimentation. There are a lot of organizations that don't have the culture of we're going to do something the way that we've done it. We're also going to try a couple of bets on the side to see if we can do something differently. And making it such that achieving an objective, to a particular degree and is job well done is very different than you need to have achieved something to a given degree, but also have been constantly evaluating other paths, other ways to improve, and that has to there has to be buy-in from the top, and frankly that helps. I would argue that helps build a good organization because you actually start having folks having interesting ideas, pushing things up. So explicitly incentivizing that within organizations is something that I've seen be successful. And the third thing, and I think this can be particularly difficult on the government side at times, is creating incentives for leaders to be technical people. That, not all of them by any means, but you'd certainly want some folks who have a technical background in leadership where they're not just advising and assisting, where they're actually making decisions. And that requires, to help change the culture, to help say, look, here's where the technical vision is, here's where we're going. That requires not just identifying those people and giving them a path, but it also requires training them in some ways where we traditionally have an issue in the technical communities where we train engineers to say, other smart people will tell you the things to do, and you just build a black box to do it. That doesn't work if you're going to actually try to drive organizational change. And so creating those incentives for technical folks in leadership is important.
You've got to be intentional. You really have to create a program around this and tell the organization, this is where we are today, and this is where we're going to be tomorrow, and this is how we're going to go do this. And then, I agree. I mean, we are an engineering company, and we believe that the nerds will win. And that's why we at the end of the day, we're hiring basically only people who have an affinity to technology. And so you cannot be successful in this company to not adopt this and not to embrace this. This is just not possible anymore. And that's it will take time, however. But but you got to be intentional. And then after a couple of years, you look back and think, well, we came a long way here.
These are all great insights.
I'd like to add one thing to that, if I may. This is a personal discovery I made over my career. And part cultural change is negotiation. And I found to be effective negotiators understand the other person's fear and address it. Addressing somebody's fear will make them more amenable to the carrot. If the carrot's there, but they have a bigger fear, you'll never get them to take the carrot. Doesn't matter how shiny that AI thing is or that digital tool is. Address the fear, understand what their fears are, and then overcome them. It's different for every situation, but that is how I personally have built up my network, my cadre. I call it my spy network because people come and tell me things because they know I'll go and figure out how to get over the their boss's fear or their opponent's fear or whatever. But if you address fears, that's far more powerful than almost any other negotiation tool. And that, to me, that's how I have changed culture over the years. So.
I remember we were talking about that before too. Man, I have all these other cards and we have 1 minute left. If anyone has questions, feel free to come up afterwards. These were great insights. What I got from this session was this is a really exciting time. There's a lot around digital engineering and the impact strategically through the tactical continuum. And at the end of the day, it does require intentionality. This could easily be a black hole from an investment perspective, so lean into those fears, create intention around those fears, and execute with the broader workforce to bring them along. So I just want to thank you all so much for participating. Thank you, everyone, for being here. It was a great session, so thank you. We have the networking and exhibits break in the Maryland foyer.